This is the third part of Experiment 5 of Make Electronics Second Edition by Charles Platt. Let's make a battery. In the first section, we talked about units and unit conversion in general. And in the second part, we actually built a battery, measuring the open circuit voltage and short circuit current. In this final part of both the experiment and of chapter 1 of the book, we're going to do a little bit more of a mathematical treatment and develop the ideas of energy and power a bit further. The main takeaway from this lecture is the concept that power is the product of two separate quantities we've been studying, the current and the voltage. Specifically, if you multiply the current times the voltage, you get the power in a circuit, and that's represented by the mathematical formula P equals IV. Remember, I is the symbol for current, and of course, V is for voltage. If we use metric units, we find that the units can simply be inserted into the equation. And so if we have a current in amperes and a voltage in volts, the product gives us a new metric unit of watts, something you might be familiar with from everyday life, and watt is the metric unit of power. In our experiments, we've seen the difference between voltages and currents from different sources. So here I show a very small waterfall to demonstrate the idea of a low voltage, small current circuit. Small current because not much water is flowing, and low voltage because the waterfall isn't very tall. I think about this as being just a small battery, perhaps a double A. Small current and small voltage. Now here is a different sort of waterfall, very tall, several tens of meters high, but it doesn't have a whole lot of flow. You can see that just a little bit of water is flowing into the pond below. And so we'd say that this would represent a high voltage but small current source of water. And this would be represented by, for instance, stacking a bunch of batteries to get to a higher voltage, something you're familiar with doing from, say, taking apart a flashlight, seeing a whole bunch of batteries stacked up, or from what we did in the last laboratory, which was take a whole bunch of lemons and string them together using different nails. Remember, nail to penny, penny to nail, etc. Here is yet a different situation. This would be low voltage, but a large current. A rapidly flowing river, wide, lots of water coming through, but not dropping very much at all. And that would be similar to the situation shown here on the right, which is batteries stacked not vertically, but horizontally, to give you either greater current or to provide a given amount of charge over a longer period of time. Finally, here is Niagara Falls, shot from a drone. You can see a very high voltage, large current waterfall. So this is lots of batteries stacked very high. We can represent these situations on this graph of voltage versus current. So voltage is on the vertical axis, and current is on the horizontal axis. The product of the two of these gives the power. And so when we start here at the bottom with the small waterfall, this is a situation of, again, low current, low voltage. And at the far edge of the graph, Niagara Falls, here we have high voltage and high current. So what is power? Power is the multiplication of these two properties in such a way that it increases diagonal to the graph. The situations shown off diagonal the high, tall waterfall with low current and the wide, low waterfall are intermediate cases of intermediate power. Clearly, Niagara Falls has a lot more power than the small stream. Let's go over the units and equations so far. Um, we have V equals IR, or Ohm's law, which applies specifically to resistors, but to many other substances in general. And V over IR can be written in the two ways underneath it using algebra. Either current is voltage over resistance, or resistance is voltage over current. And today we've introduced power as the product of current and voltage, the rate at which the river is flowing, say, multiplied by the height. And using the equations on the left, these formulations, we can algebraically rewrite P equals IV in two alternate forms. Again, the forms underneath here are simply the same concept, but rewritten using different variants of Ohm's law. For instance, since power equals current times voltage, if we take V equals IR, our original expression of Ohm's law, and plug that in for V, we get I times I, or I squared times R for the power. And similarly, you can use the third form of Ohm's law to get P equals V squared over R. So these tell you the power that you would get from resistors. We say dissipated by resistors. We'll get to those words in a moment. Under different situations. And here's a summary of the quantity, the symbol, and the metric unit. So for voltage V, we have volts, current I, amps. Resistance R, we have ohms. And then finally, here at the bottom, for power P, our new unit today is the watt. Let's do an example problem to show how these formulas are used. Let's presume that we have a very simple circuit, which is nothing but a 9-volt battery, and then we've just attached across the terminals, say using test leads, a 5.6 kilo ohm resistor. And so the questions would be, first of all, how much current flows through the circuit? We already know how we would measure that by breaking the circuit, inserting an ammeter or current meter into the circuit, and then selecting the proper range. So this is something we know how to test, part A, how much current flows in the circuit. And then a second question is how much power is dissipated when the current flows in the circuit. Let's do the first part of the problem, then talk about current dissipation. So for part A, we use the form of Ohm's law, which is written as current equals, because current is what we're looking for. So current equals the voltage over the resistance. And then we just have to plug in the numbers that we have. So 9 volts is the voltage, and 5.6 kilo ohms, and I've used the identity a kilo is times 10 to the 3, or times 1,000. Notice how I've kept the units in my equations. I always, again, keep the units in my equations as I go in these physics problems as a check and to make sure that I get the right unit at the end. So it's 9 volts over 5.6 times 10 to the 3 ohms. And if I do the math in a calculator, I would take 9 and divide it by 5.6, and that gives me the number 1.6. The 1 over 10 to the 3 becomes 10 to the minus 3. And a volt per ohm, because these are metric units, simply follow the equation. A volt per ohm is a voltage over resistance, and therefore it has to be the unit of current, the metric unit of current, an ampere. And 1.6 times 10 to the minus 3 amperes is 1.6 milliamps, which of course would be the sort of number we would be able to measure on our meters. Now let's talk about the power dissipated in the circuit. So first of all, what does this mean? Remember a little battery we imagine and just a resistor connected across the terminals. And current's going to flow, but it's not going to flow unimpeded. It's going to have to do some work to get through that resistor. Now we know when there's a lot of current where that power goes, because we've held our battery and the wires to our battery actually getting warm. So in general with a resistor, unless it's an LED or something very specific designed to have a particular sort of function, what's going to happen is that the resistor will get just a little bit warm. That's something to keep in mind as we get into more advanced circuit designs, that resistors get warmed by current flowing through them, just from the friction of the flow of electrons through that pipe, if you will. So let's use the current that we calculated in part A. So that is our 1.6 milliamps, and substitute that in to our power equation. Take 1.6 milliamps times 9 volts, gets us 14.4 milliwatts. Where does the milliwatts come from? Well, the milli carries through with the unit. Remember, all milli means is times 10 minus 3, and an amp times a volt is a watt, because the metric units simply follow the equation. Second method seems a little bit more complicated, but in fact, we'll step through it here, and it's not quite so bad, because you actually don't need the first result. We simply use the form of the power equation that P equals V squared over R. So that's 9 volts squared. Now note both the 9 is squared and the voltage is squared. The units also get treated by arithmetic operations. And at the bottom we have 5.6 times 10 minus 3 ohms. So 9 squared is 81. The unit is now a volt squared, and we still have the resistance in the bottom. Well, 81 divided by 5.6 gives us 14.4. And the V squared over ohms has got to be a unit of watts, because, again, it's metric units, so it's a watt. And the 10 minus 3 comes from taking the reciprocal of 1, by taking the operation 1 over 10 to the 3, 10 minus 3. And of course, 10 minus 3 is nothing but a milli, so our final answer is 14.4 milliwatts, same as in part B. But to give you an idea, milliwatt won't make a resistor very hot. The resistors in your kit are by and large either quarter watt or half watt resistors, meaning that they don't really get appreciably warm or in any danger of melting, as long as the power in them is less than, say, 0.25 or 0.5 watts. Well, this is 0.014 watts in this case, so we don't really expect to see this resistor getting very hot. We would say that the resistor rating is within the power limit of these currents. So let's talk a little bit now about the concept of energy. The book has this really interesting diagram which represents a reservoir which is emptying at some rate, and water is flowing out, and it's spinning a wheel. And we said that this spinning wheel is something like the current meters that we use, right? They are paddle wheels that measure the flow of current, and you don't want them to have very much resistance, because you don't want inserting a current meter to change the flow of electricity to the circuit. You want to be able to measure your circuit without actually changing its properties. So the paddle wheels, the current measuring devices, or when you're on the current setting your own meter, has very low resistance. And that's why I always set a current meter to have the current run through the meter. Remember, you interrupt the circuit and then you insert the current meter into the circuit. So here's an example of a reservoir, and we'll look at this video a couple times. Here's a dam specifically, and you can see on one side of the wall there is a very high level of water, and the other side is very, very low down there, right into wherever the water is going to spill out of the dam. So you can imagine that in this situation, our reservoir is quite large, and so tapping a small hole in the side is not going to change too much the amount of water in the reservoir, nor the amount of water downstream. Whatever does come out, you presume you're taking it out slow enough so that you're able to continue getting work out of the system, which means current flowing through and doing some work and then going to the lower reservoir. You're presuming that you're able to replenish that somehow as fast as you're taking work out, right? If this tank was allowed to run out, the voltage would drop and you wouldn't be able to push the same amount of current out of a given size hole or resistance. Now in a battery, we know the reservoir is quite large, but if you put a big enough hole in the side of it, you can drain it. If you have a battery like our lemon, you know that after a little while, you're going to run out of available sites for the electrons to come off of because of corrosion on the nails and so forth, that you're not going to be able to replenish it forever and your reservoir will slowly dip. What happens in the case of the dam where there is a small hole in the size of the reservoir? Well, you're relying actually on solar energy. In fact, you're relying on the sun to evaporate the water out of anywhere around and deposit water back in the top of the reservoir or the watershed that fills the reservoir in the form of rain. And so there is some sort of process that goes on to keeping it topped up. What about the electric power company? What happens there? Well, here's another figure from the textbook, and next to it, a diagram of a electrical power generation dam actually in process. And so what you can see is that power is being generated, current is flowing, and certainly the electric company always hopes that there's enough water behind that reservoir that it's able to turn its turbines and produce energy. In the case of a wall plug, 120 volts AC in our walls, which again is one thing you certainly should not be doing in this class, is using anything plugged into the wall outlet. What's happening there is that the electric company has to keep a particular voltage potential. In other words, the electric company absolutely must keep a certain height, if you will, pressure, so that you can put arbitrarily large current draws or large resistors up to a safe point and draw out current to turn on all your devices. So you don't make a mistake. A fuse is put in the device or a circuit breaker in the wall so that you're not allowed to put too large a hole. But the electric company actually has to always provide this 120 volts. So that means they have to carry extra capacity, have extra power plants that are capable of being turned on a moment's notice to peak up the voltage in case suddenly there's a large power draw, such as on a hot afternoon in Chicago when everyone turns their air conditioners on. Now, your voltmeter is going to work very differently than the current meter. Remember, the current meter is inserted into the flow to measure the current going past. How would you measure the height inside this reservoir? What would you do? Well, again, this current model gives you an idea of how that's done. You would take a very tiny hole, in other words, a very large resistance, and you would punch a very small hole in the reservoir and see what is the pressure behind it, how fast that water flows out. So therefore, voltmeters are used across circuits. A voltmeter connects from some point in the reservoir down to ground, and it allows just a tiny amount of water flow so that it also doesn't drain the reservoir or affect your circuit. So voltmeters have very high resistance, typically 10 mega ohms or more, whereas current meters in that mode have very low resistance, and this is why often there's two separate ports in your meters, or at the very least, the need to change the knob setting to move from current to voltage. What happens if you use a voltmeter for measuring current or a current meter for measuring voltage? Well, if you try to measure in a current meter across a circuit, that's like taking a functioning circuit and putting a huge hole and allowing all of the water to drain not into your circuit, but through the meter. And this is why your meter has a fuse and why you'll blow it if you actually try to keep your meter in current mode while measuring the voltage across a component in your circuit. We'll practice a bit more with these concepts as the class goes on. Power has then this definition in terms of energy. Energy we can think of being the total amount of ability to do work that is up in that tank. And it's the energy that you take out divided by the amount of time. That is, if you have a certain amount of energy that's being held, how fast it's released, how quickly does it go through the circuit. And we'll see that this is very compatible with our idea of voltage times current over the next couple of chapters. In metric units, power, of course, is in watts, And it turns out that the metric unit of energy is the joule. The metric unit of time, conveniently, is the second. We know that the metric system is sometimes called the MKSA system, as I said in the 5A lecture, for meters, kilograms, seconds, and amperes. So far we've come into contact with two of the fundamental units in the MKSA system, seconds and amperes. Powerlifting is a great example of high power and low energy. Right here, the weightlifter quickly yanks up a weight in just a few seconds. Now, this exercise probably doesn't burn very much energy done on its own, because although the power lifter is lifting very quickly, he is not able to maintain that effort for a long period of time. So we'd say this is a lot of power because it's a modest amount of energy in a very brief amount of time. When you divide something by a small number, the result is something quite large. Now, here is some runners at the end of a long-distance triathlon. It's quite the opposite of powerlifting, certainly. They're burning a lot of energy throughout the duration of their race. The race takes a long time, and even though they burn a lot of energy, their average power output isn't all that much. But they keep going and going. And so at the end of the day, they've actually burned a lot more energy, used up a lot more energy, and in fact, done a lot more work in total than the power lifter. Even the power lifter was producing far more power. So here's the units and equations for power and energy. Our definition of power is just the energy over time. We use E for energy often, but not always in physics, and usually T for time. So P equals E over T gives us that relationship. Remember, power is the rate at which you burn energy. Rearranging this algebraically would say the energy is the power times the time, or time is the energy or power. We'll go over a few examples of these with numbers in just a moment. And our units are power P is in watts, energy E is in joules, and time T is in seconds for the metric units. Power in particular is one quantity where we'll find power and energy metric units are not always in use. So let's do an example using power and energy. So a 40-watt light bulb would be the actual power rating on a classic incandescent light bulb that you would screw into the wall. 40-watt light bulb is only moderately bright. These days, our light bulbs are often made of LEDs or fluorescent lighting, which they'll say has the brightness of a 40-watt light bulb, but in fact use far less energy. So let's presume we have a light bulb that's labeled as it is, which actually is 40 watts. So old-style incandescent light bulb. Let's say you turn one on or leave one on, might be in a bathroom, for instance, for 3 hours. How much energy do that require? How much energy do you burn? How much energy are you going to pay the electric company for? Well, you say energy is the power times the time. So you choose this form of the law because you're looking for energy. And 40 watts times 3 hours, 40 times 3 is 120. And the unit is a watt, which you carry over to the answer, and an hour, abbreviated HR. Now, when units multiply, we usually use a time signal, a symbol, or a little dot, or something like that to indicate it's a watt times an hour. The problem is that this is not a metric unit. Remember, hour is not the metric unit of time. It's seconds, the S in MKSA. So a watt hour is a fine unit, but it's not metric. And 120 watt hours is a fine answer, but it's not a metric answer. So let's do that conversion using multiplication by 1. So take 120 watt hours. You can divide any quantity by 1. It remains unchanged. Then we're going to multiply it successively by 2 factors that are equal to 1. So 60 minutes is equal to 1 hour. So a quantity divided by itself is 1. And 60 seconds is equal to 1 minute. A quantity divided by itself is 1. So these two things are not changing the fundamental meaning when we multiply them by the quantity we start with, which is 120 watt hours that came from this energy calculation. We use multiplication by 1 by cleverly deciding what to put in the numerator and what to put on the denominator. We'd like to get rid of that hours because that's the non-metric unit. So we put that in the bottom, which means we have to put 60 minutes in the numerator. Then we're stuck with minutes in the numerator. How do we get rid of that? Well, we choose a multiplication by 1, which gets rid of the minutes and replaces it by seconds. And so the hours cancel, the minutes cancel, and we're left for units, seconds, which we bring over, and then watts is still left, so we bring that over. So it's a watt second, and going to our calculator, it ends up being 432,000 watt seconds. Now, watt second, those are metric units. So we know that we get a metric unit out, and a power times a time is an energy, and so it's 432,000 joules, or 432 kilojoules of energy that's used. Wow, that seems like a lot for leaving a fairly dim bathroom light bulb on for 3 hours. This is one of the reasons why we often see non-metric units in everyday life for energy. Can you imagine if the energy company was charging you for 432,000 joules just for having a light bulb on for a few hours? It would seem a little bit upsetting. It'd be a lot of zeros to keep track of. And so the electric company uses instead the non-metric unit of thousands of watt hours or kilowatt hours on your electric bill. It turns out that 1 kilowatt hour is 3.6 megajoules. And you can actually figure that out using multiplication by 1. If you need more practice, you can actually determine this using the method I showed. But 3.6 megajoules, or 3.6 times 10 to the 6 joules, those are the units of energy that are actually on your electric bill. Similarly with food, if you found out how many joules were in a typical candy bar, it would be a frighteningly large number. And so, in part for marketing purposes, they use the kcal or calorie as the unit of food energy. We're all familiar with looking at those food calories, and it turns out to be 4.184 kilojoules. So 4,000 joules in just 1 calorie of food. There's another example of a non-metric unit of energy in everyday life. On your gas bill, there's even a larger unit of energy typically used called the therm, which replaced an earlier related unit that was more or less energy-like called the British thermal unit. And it's 105.5 million joules is 1 therm. So you're burning a lot of joules when you're keeping your house warm this winter. And then finally, a really massive unit of energy we'll have heard in the context of explosions is a kiloton of dynamite or TNT. So this is used to classify, say, nuclear explosions. Early or small nuclear weapons were a few kilotons of TNT, and 1 kiloton of TNT is about 10 to the 12th joules. That's about the energy it takes actually to fly an airplane across the ocean over several hours. When that same energy is released very quickly, it's the kind of explosion that can destroy a city. This was taken advantage of course, by the terrorists on September 11th, 2001, who released all the energy of a transatlantic flight on the Twin Towers of New York in just a few minutes rather than over the course of many hours. Again, exhibiting that difference between power and energy. The power had incredibly destructive power because that large amount of energy was released in a relatively short amount of time by an explosion. Okay, here's the assignment, the final assignment of Chapter 1. And it's a series of equations I would like to put in your logbook. For starters, I'd like you to go back and take your data that you just collected in experiment 5B on the 3-lemon battery. The maximum power output from your battery we can estimate to be the short circuit current times the open circuit voltage. It's the maximum power that your battery can produce. In reality, the max of power actually produced is always less than this, because typically there is a resistor. It's not just a short circuit or an open circuit. So this is a maximum power that your battery could produce using P equals IV. And then consider that your battery with a lemon might possibly run for an hour before the nails get too corroded. And so I'd like you to calculate what the total energy produced is. And I'd like you to do it in two different units: the non-metric unit of watt hours and the metric unit of joules. Both these are the same quantity, just expressed in two different units. And then I'd like you to estimate the cost per watt hour. Remember, a watt hour is the unit of energy, so that's the cost per some amount of energy, or dollars per watt hour, for your battery. This should, of course, include everything you used. The pennies, of course, that's 3 cents, but also the nails, wires, and lemons. So the cost of producing that amount of energy from your lemon. And then I'd like you to compare it to your electric bill. Try to figure out maybe if you should be buying lots of lemons and pennies and nails, or continue paying the electric bill. So get a copy of the electric bill from your home. Please do attach a copy into your lab notebook so you can take a quick look, make sure that you're doing the calculations right. And try to figure out how much energy you use for the particular month. And I don't care what month you look at. It should, by the way, be an electric bill and not a gas bill, or just use the electric part if it's a combined bill. The energy used for that particular month will be given probably in kilowatt hours, that non-metric unit. So convert that to watt hours. You have to use multiplication by 1, and then also convert it to joules. And then finally, using the watt hour measurement from your electric bill, please compare the cost of generating energy from your lemon battery versus what you pay on your electric bill. And again, let me know if you think you should be buying more lemons and nails, or continue to pay the electric company. In Illinois, of course, most of our electricity comes from about 50-50 nuclear power and coal.